Hello everyone, we are Team Vicharaka, the Mars Rover team of IISc Bengaluru. For URC 2025, we are proud to present our first generation Mars Rover, Vicharak. Our mechanical system features a robust 6-wheel differential rocker bogie suspension engineered for superior mobility across challenging terrains. The chassis is constructed from aerospace grade 6061 aluminum fabricated using laser cutting, welding and precision machining. Designed for rapid assembly and disassembly, the entire structure weighs just less than 50 kg with a compact yet stable wheelbase of 93 cm by 84 cm. The system can effortlessly traverse rugged landscapes, tackle steep inclines of up to 50 degrees and descend near vertical drops with stability. The wheels are specially designed for maximum traction across diverse terrains, fitted into custom hub and bearing assembly using a combination of metal and 3D printed parts. The aluminum extrusion chassis has been rigorously tested to withstand loads of up to 150 kg, ensuring durability and reliability under extreme conditions. Powering this system are mega torque 34 Nm planetary geared DC motors delivering the necessary torque for smooth and controlled movement in any environment. This design seamlessly blends strength, agility and modularity, making it ideal for navigating Mars-like terrains reliably.
Our Rover's electronic subsystem is designed with a robust and modular architecture to control and power efficiently all the electronic subsystems present in the Rover. The main power distribution board is a custom-made hand-soldered one that integrates individual motor current measurement and fail-safe system to enhance system's reliability. Powering the main power distribution board is a STM32 microcontroller that also includes undervoltage, overcurrent and thermal failsafe mechanisms. The Rover is powered by a 21 amp hour 24 volt lithium ion battery, providing over 180 minutes of runtime with all subsystems operating simultaneously. To drive the 18 volt motors, we utilize 300 watt buck converters along with 30 amp brushed DC motor drivers, delivering stable and efficient power. All electronic boards are modular and easily swappable, allowing for quick replacement in case of any failures, ensuring minimal downtime and easy maintenance. The TNZ 4.1 microcontroller handles the lower level tasks and communicates with the main power distribution board via UART, enabling supervisory control of the power distribution system from the base station. The motor control system is implemented as a closed loop PID system, ensuring precise rotational speed and torque control for each wheel, thereby improving Rover's overall efficiency and maneuverability.
We are performing 3 chemical assays indicative of the presence of life: Bradford's test for proteins, Sudan test for lipids, and litmus test for ammonium salts. In the Bradford's assay, the solution changes from brown to bluish upon protein interaction. On the other hand, Sudan test detects proteins through visible phase separation. Presence of ammonium salts is detected by the change in the color of litmus paper. These results are then visualized by a camera.
We are currently building a modular custom-built Raman spectroscope for the detection of organic molecules and analysis of minerals present in the soil sample. The spectroscope consists of 2 major parts: a spectrometer unit and a fiber optic coupled probe. The spectrometer unit has a 532 nanometer green excitation laser and a CCD array detector. This is coupled by a fiber optic probe to a probe which is used for both collection and excitation of light. To detect organic molecules, we will be looking for peaks in particular ranges associated with common functional groups, and minerals will be detected by checking for peaks in a different range.
Our sample collection system features an auger drill mounted on an actuating platform, driven by lead screw mechanism and controlled by stepper motors. To prevent surface contamination and ensure exclusive sampling from depths beyond 10 cm, a protective sheath covers the auger until it reaches the target depth. At this point, a linear actuator retracts the sheath, exposing the auger's slits for soil intake. A custom suction pump then transfers the fine samples through a pipe junction, distributing them evenly into 4 separate collection containers, minimizing cross-contamination. One of these containers stores dry samples for retrieval and analysis at the base station. The remaining 3 receive chemical reagents via peristaltic pumps. A stepper gear mechanism ensures thorough mixing before transferring the solution into a cuvette carousel, which holds quartz cuvettes. The entire system is modular, enclosed, and constructed from black PLA to minimize external light interference and scattering. A camera monitors the color changes. We use Theramino spectrophotometer software to analyze the results and detect the biomolecules. For additional analysis, a sensor probe lowers into the containers to measure pH. In the dry sample container, an NPK and moisture sensor is used to get the data of soil moisture, temperature, and measurement of the levels of nitrogen, phosphorus, and potassium in the soil, essentially indicating the soil's fertility, which are key indicators of potential biological activity and presence of life.
Additionally, we are working on integrating a microscope and spectral sensor along with filterable databases to understand the rock composition. For the geological history of a region, we would use high-quality onboard cameras to visually analyze stratigraphic profiles across the terrain.
The Rover features a 5 degree of freedom robotic arm. The main base elevation and elbow elevation joints are powered by 1500 Newton linear actuators, allowing accurate control with high payloads. A 2 degree of freedom differential wrist mechanism reduces the complexity of the design by combining the wrist elevation and wrist rotation joints into one unit. The gripper features a pointer which is used to type on keyboard and press various buttons. Both the gripper and differential wrist are controlled by modified servo motors. Optical encoders are used to implement PID algorithm, and real-time servoing is done based on the video feed received from the cameras mounted near the end effector.
The top part of the robotic arm, we have a bevel gauge differential which is powered by DC motors. They have 60 kg centimeter torque rating each, and the torque is quadrupled using a spur gear set. The gripper part consists of a rack and pinion mechanism. The pinion has a 60 kg centimeter servos, essentially providing us with a 300 Newton grip force, and we have rubber attachments to the end effector to increase the friction while grabbing stuff, and we have a stick type attachment to press on keyboards, and we are essentially planning to add a LiDAR and a webcam to type autonomously in a keyboard.
Its 5 degrees of freedom gives us a huge reach covering a meter above and half a meter below with respect to the top of the chassis. 2 linear actuators, one at the shoulder joint and other at the elbow joint, allow precise control of the arm by providing a maximum thrust force of 1500 Newton. The actuators measure 50 cm when fully extended. The lower arm joining the base and the elbow joint measures half a meter. The upper part together with the gripper has a reach of 80 cm. The base is supported by an aluminium shaft of diameter 25 mm held down using flange bearings. The shaft is rotated using spur gears attached to a BLDC motor which can provide a torque up to 15 Nm using a planetary gearbox.
Our robotic arm uses 12 volt linear actuators which are driven by Cytron MD30C R2 30 ampere motor drivers. For the base motor, we require an 18 volt supply which is provided through a buck converter. This ensures stable voltage and regulation and optimal performance. To manage all these components efficiently, we have designed a custom power distribution board. This ensures that power is delivered safely and effectively to all the actuators, preventing voltage fluctuations or power losses. For manual control, we have integrated the FlySky FS I6B transmitter receiver set, allowing an operator to directly control the robotic arm wirelessly.
The Rover is designed for fully autonomous navigation, integrating multiple sensors and uses advanced decision-making algorithms to traverse complex terrains. Built on ROS2, the system processes sensor data in real time, enabling localization, mapping, and path planning for obstacle-free movement. At the hardware level, the Rover is equipped with a Pixar flight controller with a built-in IMU. The Pixar is connected to a M810 GPS sensor and a TNC microcontroller for motor control and sensor interfacing. Additionally, a depth camera and a LiDAR are used for obstacle detection and localization. The depth camera also features a built-in IMU. For perception and mapping, the LiDAR and depth camera, integrated with appropriate ROS open source packages, processes point cloud data and laser scan data for SLAM, allowing the rover to dynamically map its environment. An extended command filter utilizes IMU data from the Pixar and depth camera along with wheel odometry and GNSS data from the M810 GPS sensor to accurately localize the rover both locally and globally.
For autonomous navigation, we have two algorithms running on the rover. First is global path planner and second is local search algorithm. A policy deciding algorithm manages the execution and mode of these algorithms. For global path planner, it utilizes current GNSS coordinate and target GNSS coordinate initialized by the policy deciding algorithm to send appropriate commands to control system. Once rover reaches its target GNSS coordinate within an appropriate threshold, it switches to local search algorithm. The local search algorithm operates in two modes: Aruko marker detection using OpenCV and object detection using a fine-tuned YOLO V8 model. The local search algorithm performs a spiral search in its neighborhood until it detects a marker or an object. Once detected, the pose of object is determined using 3D PNP and the rover navigates towards the calculated location. If marker is lost during the motion, the rover follows the calculated trajectory for a while before restarting the spiral search. Upon reaching the object's location within a distance of 2 meters, it updates the state and transition back to the global path planning algorithm. If marker cannot be located, the rover moves to the next target coordinate and marks the previous coordinate as incomplete for future revisits. We have tested the algorithm in low light conditions and cluttered environment with high success rate.
The rover can be controlled in two ways, via joystick control in ROS or using a SkyDroid controller. If communication between the base station and antenna is lost and manual joystick control is not feasible, the SkyDroid controller serves as a backup with tested functionality extending from 650 meters to 2 kilometers beyond the line of sight. With its robust sensor fusion, mapping and path planning capabilities, the rover can autonomously navigate diverse terrains while dynamically adapting to obstacles. The integration of ROS2 ensures modularity, scalability and efficient execution, making the system reliable for real-world autonomous navigation in uneven terrain.
We sincerely thank Art Park and RBCCPS for their generous sponsorship and support in making our Mars rover project possible.